So now that we've set up our DP table and we know what DP of I of j represents, we know why most of our elements are zeros. We start filling the table because obviously that's the next step in any DP solution. So now in both the examples you saw previously, coin change and longest common subsequence, we started top left to right and then second row left to right and so on. Here however we'll start filling the table diagonal by diagonal. So if you go back here, we'll first fill DP1 of 2, DP2 of 3, DP3 of 4, then 1 of 3, 2 of 4 and finally 1 of 4. This is the order in which we will fill for matrix chain multiplication. Now why is that? Because again, to answer that question, we go back to our definition of DPIJ, which is the minimum multiplications required to get the matrix product from AI to AJ. Now if you take DP1 3, it's going to be the product of three matrices, A1 into A2 into A3. To find the minimum multiplications required in a product of three matrices, you first need the minimum multiplications required for combinations of two matrices. So if you have A into B into C and you wanted to know whether AB into C is better or A into BC is better, then you should first know AB, BC. Only then you can do, like, so you go back to this thing, we knew AB is some this much and then we did AB into C and we got 75,000. Similarly here we knew BC is some 13 to 14 to 10 whatever, then we did some multiplication or some manipulation on it and we got 32,000. And that's the whole idea of DP, right? Overlapping subproblems. So if you want the solution for a sequence of k matrices, you should first know the solution for a sequence of k minus 1 matrices. So every diagonal here represents a sequence with a specific number of matrices. So if you look at 1 of 2, it is just A1 into A2. 2 of 3 is A2 times A3. 3 of 4 is A3 times A4. So the first diagonal there, every element there is going to be the product of just two matrices. Next, if you take this diagonal, 1 of 3, it's A1 times A2 times A3. This 2 of 4 is A2 into A3 into A4. So every element on this diagonal is going to be the product of three matrices, and this one finally will be the product of four matrices. So to know the minimum for four matrices, you need the values for three matrices, for which in turn you need the value for two matrices, which is why we start filling diagonal wise. Right, so now we know that we have to fill in the values diagonally. The next and most important sequence, step in the sequence is to come up with the optimal substructure, which is the formula using which we will fill in the table. Now, so this thing we find in the box here is the optimal substructure. DP of I of j is 0 if I greater than equal to j. This is what we saw, all those zeros we filled in. If I equals to j, it's just the matrix, no multiplication, so 0. If I greater than j, it's like A2 times A1, which is not defined, so it's 0, and so on and so forth. For the valid grids where I less than j, or when the grids belong to the upper triangle, the value of that grid is defined by this formula: dp of I of k plus dp of k plus 1 of j plus p of I minus 1 into p of k into pj, where k is any value ranging from I up to j, I included, j not included. So I know this sounds very abstract, just a mathematical equation at this point. I'm going to break it down for you. I will first, let me first quickly reiterate what this pi pj is. P is the array of dimensions that you had. So this 30, 35, 15, 5, 10, that is your array P. So pi minus 1 would be the I minus 1th element of this array, pk would be the kth element, and pj would be the jth element. So this part is clear. Now why do we take this k ranging from I up to j, and why is I included, why is j not included, and why do we choose the minimum value among all these, and what is the meaning of this whole expression? So if these are some questions in your mind right now, let us dive into those right now. So what is this k first of all? So k is any value which lies between I and j minus 1. It can be any value from I up to j minus 1, which is what this thing means, right? I less than equal to k less than j. So if j is not included, then the maximum it can take is j minus 1. So So what this K physically represents is, and I will request everyone to pay close attention here, what this K represents is one of the intermediate matrices from your AI plus 1 so on up to AJ, one of those intermediate points where you are going to break and put the parenthesis and regroup. So for instance, going back to this thing, A, B, C, you have 3 matrices. So let's say your I is 1 and C is 3 because you want to compute the optimal order of multiplication for matrix 1 into 2 into 3. So your I is a 1 and J is 3. So at this point, if you see, after B, we are breaking the product and we are regrouping AB as one term and C as another term. So here K is 2 because 2 elements become one term and the third element becomes another term. Whereas if you look here, after A, we are putting a break. These two become one, let's say one entity, and this becomes one entity. So K here is 1. So what we mean by K generally is when you have matrices from I to J, AI into AI plus 1, so on into AJ, at whichever point you choose to break and you group from ith to this point is one group, from the next one up to the jth is another group. I will compute this product separately, then I will multiply them both. That breaking point is what is called K. So that's the first question, what K is supposed to represent. Now moving on to why K is given this specific range, I less than equal to K less than J. Obviously because the matrices range from AI to AJ, K has to lie within there somewhere. And K cannot be equal to J because if K equal to J, then you are splitting after Jth matrix, which means you are not doing any split at all. So if you take this A into B into C, if I say K equals 3, then I am putting a split here after C, which means I am literally not splitting anything. It's still A times B times C. So K can be anything from I up to J minus 1. That is why the range of K is defined as such. So now you know what K represents, which is that intermediate matrix at which we split. You know why K is defined within a specific range, which is I to J minus 1. Okay, now the only thing which I have to clarify with regards to the optimal substructure is why this formula. So now, keeping in mind the definition of dPij, which is the minimum number of multiplications required to perform AI cross AI plus 1 cross blah 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 up to AJ, this becomes very simple to understand. So dP of I of K will be the minimum multiplications required for the subproduct AI into AI plus 1 up to AK. dP of K plus 1 of J is the minimum multiplications required for the smaller product AK plus 1 into AK plus 2 up to AJ. And then this term Pi minus 1 Pk Pj is the product of these two matrices. So let's say you have A into B into C into D, 4 matrices. And if my K is equal to 2 for instance, meaning after B you are splitting. So AB is going to be one subgroup, CD is going to be one subgroup. Then dP of I of K is going to be the minimum multiplications required for AB. dP of K plus 1 of J is going to be the minimum multiplications required for CD. And then you have two products now, AB and CD. Now you have to multiply those, right? AB times CD. For that, it is Pi minus 1 into Pk into Pj. So where did this come from? It comes from this rule, this one statement with which we started our entire discussion on this topic. So if you have done this, dP of I of K, you will have a matrix with specific dimensions. And if you have done this, you will have a matrix with specific dimensions. And when you and you will see, I'm not going to prove this mathematically because I don't want to make the lecture too complicated. But when you group the matrices I to K together, you will see that their dimensions are I minus P of I minus 1 into P of K. And similarly, when you group the matrices K plus 1 up to J together, you will see that the dimension of that product matrix is P of K into P of J. Now again, when you multiply an M cross N and an N cross P, the number of multiplications is M into N into P, which is why it becomes Pi minus 1 into Pk into Pj. So what does this expression basically tell us is, you have different values of K ranging from 1, 2 up to J minus 1. For each K, you are going to compute what is the cost to split from I up to K, what is the cost to split from k plus 1 up to j, and then what is the cost of multiplying those two split terms. So those are these three parts respectively. You add up that cost. So you compute this for each value of k ranging from k equals 1, k equals 2, so on up to k equals j minus 1. And then for whichever k this value happens to be minimum, we'll choose that k and that specific value and we'll put it in the table, because this is a minimization problem. And that means when I split the matrices AI up to aj at k, and I do I to k as one part, k plus 1 to j as another part, and then I multiply both, that is when I get the optimal multiplication of these matrices I to j. That is what this optimal substructure means.